Dear student, let us begin the lectures on machine design part 1. This is lecture number 25 and the topic is design of joints with eccentric loading. In the last few lectures, we have studied many things about different kinds of joints. Some joints are non-permanent types, that is they could be detached, for example the screws and flange coupling etc. And some are permanent type joints. Those could not be detached without damaging the components. The examples are welded joints or riveted joints. Now, in those cases we have studied only the simple type of loading. In this class we are going to study something about a complex type of loading which is known as eccentric loading. Now, let us look at the joints with eccentric loading. We have eccentrically loaded riveted joints, then eccentrically loaded bolted joints and eccentrically loaded welded joints. Now, let us come to the first case, eccentrically loaded riveted joints. Now, rivet joints, as we have studied, these are joints which look like the following. If I draw it, if we have loading here and load applied here PP, then the joint load, so these are rivets. The rivets are meant to take load primarily in shear, and here you see there is no bending moment acting on this joint, because here if we take one small section of it, that is one pitch, then the load is passing normally through the center of gravity of the riveted joints. But if it does not pass through the center of gravity of the riveted joints, that happens sometimes in the case of brackets or in some other the load carrying members, as we shall see different cases, then the loading becomes complicated and eccentric, and the stresses becomes also complicated. We have to take utmost care so that the rivet stress does not become too much. Similarly, we have the eccentrically loaded bolted joints. Now, here rivet joints mainly take load in shear. The bolted joints take primarily load in tension. You may remember we talked of the effect of pre-stress. There we had to initially tense the bolt. By initial tensioning, we relieve the bolt of the final loading if the loading is tension type, but primarily always we talk of the tensile load in a bolted joints. When we come to the welded joints, then there may be two possibilities. You remember there are two kinds of welded joints. One is butt weld, which can take tensile load as well as the shear load. So, in the butt joint we can take tensile as well as shear, but the fillet joints, there is another thing called fillet joint which can take load, or which is designed to carry load only in the shear. That is, it is not mandatory that all the loads will be shear type, but we carry the design procedure assuming that entire load is shear and acting on the throat cross sectional area. This must be very clear from the last lecture. In this lecture we are going to study something of this kinds of joint, that is eccentrically loaded riveted joint, eccentrically loaded bolted joints and eccentrically loaded welded joints. Let us now start the discussion of eccentrically loaded riveted joints. See, if we have a rivet joint of this shape, let us say this is the plate which is acted on by a force P over here, and there are few rivets. Let us say there are some rivets here, and it is connected to another plate. Now, clearly you see the cross section, that is the load does not pass through the center of gravity of the riveted joints. And what is meant by the center of gravity of the riveted joints? Now, if the cross sectional area is A1, A2, A3, AI, where I equal to 1, 2, 3 and 4, then there are the cross sectional area of these joints is given as x bar, which is equal to A1 x1, the x coordinate of the first rivet, plus A2 x2 etc., plus A3 x3 plus A4 x4, all these things will come divided by the total area A1 plus A2 plus A3 plus A4. So, this is the area of cross sections of the center of gravity, center of the geometric center of the rivets. Similarly, we have y bar, which is equal to summation A I y I bar. This x1 bar, x2 bar etc., these are nothing but the x coordinates of the ith rivet. Similarly, we have y coordinate, and if we do this, then we get x bar and y bar, the center of gravity of the entire riveted joint. Let us denote the joint, that is the center at this point. Okay. So, this is the center. Now, the load clearly does not pass through the center. So, therefore, the tendency will be first to shear off, because every bolt will take some shear load, as well as there is a tendency to rotate about the center of gravity. So, definitely there will be two kinds of loading which we are going to study. Let us come one by one. First, there will be the shear force acting. There are now 4 such rivets. So, therefore, each rivet will carry a shear force P divided by total number of rivets, which is equal to 4. Therefore, this is P by 4, and then we have to calculate the bending, the force that is acting because of the tendency of this entire plate to rotate about the center of gravity. What will be that force? That is difficult to find out analytically. So, there is no exact solution possible, but we make some assumptions. We assume that the riveted joints rotate about this point, and the load acting is proportional to distance from this CG. Now, let us look at it. If we replace this load, now it is clear from statics that within one static body we can remove this load, we can shift this load from one point to the other, provided we add some amount of couple or some amount of moment about the next new point. Let us see what does it mean if we remove this load. Now, what we have done essentially is to take the load here, so this is the load, but now we have to add again a moment. And what is the moment? The moment will be equal to, we have to add the moment is definitely clockwise, and this moment m will be equal to p times the length of the arm, and this is the distance. If the eccentricity is e, then this is nothing but m is equal to p times e. So, this moment has to be added. Now, the internal forces within the rivets will be such that they should balance not only the this external force P, but also this external moment M. As we have discussed, because of the direct load P, each of the rivet will experience some shear load, and which is equal to P divided by N, and for 4 such rivets here we have P by 4. Now, this is true for all the rivets. Now, we have to calculate the effect of the M. Now, here we make an assumptions, that is, if you look at this riveted joint more carefully, that is, if you enlarge it, etc. So, this is this part which I have enlarged. Then the center of gravity is of course here. Then we make the assumption that each one, the load carried will be proportional to the distance from the center. That is, if let us say this is F2, this force is let us say F1, and this is perpendicular to this line joining the rivet, the first rivet and the center of gravity, and this magnitude F1 which is proportional to this distance. If we denote this by OA, B, C and D, then F1 is proportional to the magnitude of F1 is proportional to OA. The magnitude of OB or magnitude of F2 that is acting on this rivet is proportional to this length OB, and the direction of this force is perpendicular to it, to the line joining OB. Similarly, on C we have F3 which is proportional to OC and direction perpendicular to the line joining OC. Similarly, OD this way. F4, the magnitude is proportional to OD and the direction is perpendicular to the OD. Now, here we make the make these assumptions, and with this assumption we can calculate further. What we see, if we denote this by R1 vector and this is R2 vector, R3 and R4, then we have the following relationship, that is F1 times R1, the couple about point O, plus F2 times R2 plus F3 times R3 plus F4 times R4, this plus M will be equal to 0. Now, this is the balance of the momentum about the point O. Now, we have made the assumptions that F1 is proportional to R1, F2 is proportional to R2. Let us denote the proportionality constant to be K. So, Fi is equal to K times Ri, where K is a constant. Now, if you substitute this into these equations, what you get is K times R1 square plus R2 square plus R3 square plus R4 square plus M equal to 0. So, this is the equation which you get. From this you can solve for K. Directly what you see is that the value of K now is, let us write down in far more legible form. What you have then, Fi is equal to K, which is equal to minus M divided by summation Ri square, I is 1 to 4, and times Ri, and this is equal to minus Pe Ri divided by summation Ri square. So, this is now the force acting on ith rivet. Now, let us see what is the resultant of this force. Remember, we have two forces. One is the force which is acting because of the shear, the direct shear, and each one is carrying same force, and there will be another force due to the turning actions. So, therefore, we will have to look into the resultant of this force. Now, the resultant will be different for different cases. We study one or two cases here. You see, for the first case, we have now here on this, let us say on the A, that is the first bolt, we have direct shear force which is equal to P by 4, and we have another one which is equal to, which is perpendicular to this distance, and this is F1. Now, we should get the resultant force. You get the resultant vectorially. So, this is nothing but the resultant force. Now, you know very well the resultant force will be equal to, if you denote this vector to be F I. So, that is the first vector. You will have to calculate the resultant for each of the rivet. So, if you calculate that, what you get is the resultant F R will be equal to, this is P by 4 square plus F I square plus twice P by 4 times F I cosine alpha, which is the angle between these two forces. So, therefore, for each of the bolt you will have to carry these calculations, if you have to make these calculations, and you will have to find the highest, the largest F R, that is the rivet which has the largest share of the load. Now, you will have to design the rivet such that the stress in the maximum stress in the bolt is below the allowable limit. So, with the help of these calculations, you first calculate what is the maximum of F R I, where I equal to 1, 2, 3, 4. There are 4 such cases. So, you get this maximum force F max, and then you calculate the stress. Now, the shear stress F max divided by pi by 4 d square, and that must be less than tau allowable. So, this is the design criteria for eccentrically loaded riveted joint. Now, let me repeat again. We make the assumption that whenever we have eccentrically loaded joint, the turning action around the center of geometric center of gravity of the riveted joint will be such that the force in each of the rivet will be proportional to distance of the rivet from the center, and the direction will be perpendicular to the line joining the point, the center of gravity, and the corresponding rivet. So, with this assumption we make these calculations, we find out the maximum force in such rivet assembly, and then with the maximum force we calculate the shear stress taken by the maximum shear stress taken by this bolt, and hence we calculate the corresponding diameter, that is we design the joint. So, this is the design procedure for eccentrically loaded riveted joints. Now, let us go to the design of eccentrically loaded bolted joint. Here we have two cases distinct. First, let us take the example. Here consider this kind of bracket. There are bolts here. So, if you look from this side top, you will see now these are bolt. Let us say cross section 1, section 2. So, there are 4 such bolt, 1 and 2, and the load is acting here. There is a load P acting. Now, you see what will be the effect of P. Now, the P will introduce tension in the bolted assembly. So, each bolt will carry some tension, but the tension will not be uniform, because there is a distinct tendency for this bracket to rotate about this point, let us say point A. So, there is a tendency that it will rotate about this point because of this load. So, therefore, the tension in the bolts will be unequal. Now, again what we see now, how to calculate the load, the tensile load in the member. We make the static equilibrium, that is, let us say that each of the bolt here carries a load F1 and F2. Now, if you write down the static equilibrium equations, then F1, there are 2 such, 1 and 2, 2 F1 plus 2 F2 will be equal to P, and that is the only static equilibrium equations we have for this case. Now, this is statically indeterminate problem, therefore, because we have 2 unknowns and 1 equation only. So, it cannot be solved by means of pure statics only. So, we will have to take help of now the kinematics, that is the flexibility of this member. Now, if you take the consideration of flexibility, we make the assumptions that here this body is a rigid body, this bracket is a rigid body. So, therefore, when it rotates, suppose it rotates, then because of rotation it will come to some this kind of position. So, because it has rotated. So, this was the original position and this is the final positions. Now, it has rotated, therefore, there is a small deflections of these 2 bolts. There will be some elongations of this bolt. If you draw it elaborately, then what you see here, this was the initial line, and after that it has rotated here. So, now if you denote this length from this point to that point by L1 and from here to there L2, then what you get is that this is L1, this point A and point B. So, this is L1 and this one is L2. Now, the delta, that is delta 1, that is the deflection of this, is now proportional to this length L1. That is clearly visible because this is a rigid plate. So, this angle is constant. So, tangent of this angle will be equal to delta 1 divided by this length L1, and the tangent of this angle will be again equal to delta 2, which is the deflections of this bolt divided by the entire length L2. So, therefore, delta 1 is proportional to L1 and delta 2 is proportional to L2. Then if you use the Hooke's law, then what you get is that F1 ultimately could be written is F1 is proportional to L1 and F2 is proportional to L2. That is clearly visible because delta 1 is nothing but Young's modulus times the original length, let us say delta is the original length and the deflection is the extension is delta 1. So, the strain is delta 1 divided by capital delta, which is equal to Young's modulus. I am sorry, this has to go down. So, this will be equal to stress, which is equal to F1 divided by A1 and E1. Now, if you consider A and E are same, that is A1 equal to A2 and E1 equal to E2, then what you see is that F1 is proportional to delta 1 and delta 1 is proportional to L1. So, therefore, F1 is proportional to L1 and F2 is proportional to L2. So, that comes from a very simple calculations. Now, what we can have is that we can use these considerations, that is F1 is proportional to L1. If you consider the proportionality constant to be k, so therefore, F1 is k times L1 and F2 is k times L2. So, in that case you can get the F So, in this case you can find out F. So, thus we arrive at the different loads in the bolted joints. So, this is one example where the load is acting. Now, load is acting such that there is always tensions in the bolt. Now, we come to the second example where the load is acting such that both the tension as well as the shear force will be developed. Let us see. Let us come to the next example. Here we have now here, and we have, let us say again some kind of arrangement. If you look from this side, then we have this bolt. So, there are this 4 bolts, the load is acting over here. So, therefore, you see the direct effect of P will be to introduce some shear force here. So, each of this bolt will carry some shear force. Now, the shear force will be equal to P shear will be equal to P divided by 4, because there are 4 such bolts. Now, what is the effect of this eccentricity? Let us say that there is a distance E from this plane to that of the applications of P. Now, because of this eccentricity, it will try to rotate about this point. Okay. If this is A and B, so there is a tendency that it will rotate about this point. Now, because of this tendency of rotations, so there will be elongations, that is enormous tensile force will be developed in this bolt. And again, if you consider the rigidity of this member, that is if it tilts, for example, here this way, so this is the tilting, it is very much exaggerated, but the point is that now the rigid body dynamics, that is rigid body statics is not enough, and we will have to consider the deflections, that is the elongations of the bolt. We will have to consider the strength of material approach. So, therefore, we make this assumptions that this is a rigid body rotations. Now, this body, the bracket is relatively rigid compared to that of the bolt. So, the bolt gets extended, whereas the rigid body gets only rotated. And here again, if this length is L1 and this is L2, what we have is that L1, that is this force, again from the same calculation as before, this force on this first bolt, that is this bolt, again will be F1, which is proportional to L1. This is why, because we see delta 1, the elongation of this bolt, that is of this bolt, the elongation will be delta 1, and this is proportional to L1, and that is because this angle is constant. Again, the tangent of this angle will be equal to delta 1 divided by L1. Again, the tangent of this angle will be also equal to delta 2 divided by L2. So, delta 1 and delta 2 are proportional to L1 and L2 respectively. Now, again if you use the Hooke's law, you get that F1 and F2 are proportional to L1 and L2. If you use this proportionality constant to be K, then what you get is F1 is KL1, F2 is KL2. Now, you have already used the equilibrium equations, force equilibrium equations, only we are left with the moment equilibrium equations. Let us use the moment equilibrium equations now. If you take the moment about this point, what you get is that F1, let us consider this direction of this force is here F1 and F2, then we have F1 times L1, the moment about point A, F1 L1 plus F1 times L1, because there are two such bolts. So, twice F1 L1 plus F2 times L2, again twice of that. This is equal to the external moment, which is equal to P times E. Now, if you use this relationship, that is F1 and F2 are proportional to L1 and L2 respectively, then what you get from this equation is twice K L1 square plus L2 square will be equal to P times E. From this you calculate K, which is equal to PE divided by twice L1 square plus L2 square. Once we have calculated K, then we have calculated F1, because F1 will be equal to K times L1. So, this is equal to PE L1 divided by twice L1 square plus L2 square, and F2 will be equal to, similarly F2 will be equal to PE L2 divided by twice L1 square plus L2 square. Now, let us sum it up. We have we have now a situation where in a bolt there are two kinds of stresses. If you consider this bolt, the first bolt, that is this one, here this is the bolt. Now, we have the force P by 4 as well as, so there will be the shear stress developed, which is tau equal to, shear stress will be is P by 4 times a bolt. So, this is the shear stress developed, and there will be the tensile force. The tensile force is again F1, which is given as PE L1 by twice L1 square plus L2 square. Definitely F2 is much larger compared to F1. So, therefore, the tensile force will be larger for the second bolt, this bolt. So, when we consider when we have to find out the cross sectional area of the bolt, that is when we want to design the bolt, then we will have to consider the maximum of the stresses. So, we consider the second bolt. The first bolt gives the tensile stress F1 divided by sigma will be equal to F1 by a bolt, but F1 is less than F2. So, therefore, the maximum tensile force will be taken by the second bolt, and we will have to consider the design with the second bolt itself, but not the first bolt. So, if you consider the second bolt, what you get is the same shear force, but here F2, tau remains same, sigma becomes, instead of F1 we have F2 and divided by AB. Now, we have the case where the bolt is subjected to both shear and the tensile force. Now, normally, as I said, the bolts are not meant to carry the shear load. Primarily, the bolts should carry only the tensile load, but if sometimes the shear load occurs, then we have to relieve the bolts of the shear load if possible. So, that is done by say adding some kind of other bolts, dowel pins, etc. So, this should take off the shear load as small as possible. So, if you increase the number of bolts over here, then the shear load may be decreased. So, this is done, the shear load is reduced as far as possible, but if further is not possible, then we will have to consider the effect of the shear stress as well as the normal stress. We have the shear stress and the normal stress, and then we calculate the von Mises stress. You know that when we have both the stresses, we can calculate sometimes the von Mises stresses, which is equal to sigma square plus thrice tau square. This is one failure criteria where the material fails if this is greater than F sigma allowable. Another failure criteria is the maximum shear stress, which is tau max will be equal to sigma by 2 square plus tau square, and this must be. So, these are the two criteria by which the ductile material will fail. If it is made of brittle material, which seldom happens, then we will have to consider the maximum principal stress, and that is given by the well known formula, that is sigma by 2 plus under root sigma by 2 square plus tau square, and if the material is brittle nature, then this should be less than allowable. So, these are the view failure criteria which you will have to consider, but the main important point is that here the bolts are subjected to both shear stress as well as normal stress, and when you have to calculate the normal stress, you will have to make these assumptions that the bracket is more rigid compared to that of the bolt. So, therefore, the bracket actually rotates about one of the points, but the bolts will get elongated and the forces will be found out accordingly using the geometrical relationship. So, that must be clear. This is again a case where statical determinacy does not exist. So, this is statically indeterminate problem, and we will have to take the help of the flexibility of the members. Now, this is about the design of eccentrically loaded bolted joint. Remember, I repeat, we have considered two cases. In one case, the load is acting such a way that the bolts are entirely under tension. There is no shear force, as we have seen from the first example. In the second example, the bolts are now under shear because of the direct action of this force, and it is again partly under tension because of this eccentricity. So, eccentricity makes the joints, the design of joints quite complicated, as you might have understood by now. So, this is about the eccentrically loaded bolted joint. Now, we come to the third case where we have the eccentrically loaded welded joint. There are again few examples. We take one by one. Let us consider the case where a plate is welded to a structure . Now, the welding can be done in various ways. The welding may be this side, that is, it may be a transverse fillet welding. There are two kinds of welding, one is butt welding and another is fillet welding. Normally, in this case we use the fillet welding. There may be again two types of fillet welding, one is transverse fillet and another is the longitudinal or parallel fillet. Let us say that here this is in parallel fillet. So, we have the fillet joints here, fillet joints over here, and the load is now eccentric loading and in these directions. Remember, in earlier classes we have studied the design of this joint, this welded joint. In that case, the load was along these directions, but now instead we have load in the other directions. So, what is the effect of that? That is what we are going to study. Now, you see here, if you look a little bit closely, then what you see, the fillet weld looks like this. So, this is the plate and this is the welded part. So, this is the fillet, and the critical section is the section of the throat, that is this section. So, this is the critical section, and the failure may take place in this section itself. Now, when we consider the eccentrically loaded joint, what we see that in addition to the shear force, there may be then two cases. There are two kinds of stresses, the direct shear force, direct shear stress, and what is the direct shear stress? The direct shear stress value is equal to tau, will be equal to P divided by twice, because there are two such wells, divided twice area of the throat. And what is the area of the throat? If this leg size is h, normally the fillets will have equal dimensions. This is this is 45-degree angle. So, therefore, the AT will be equal to throat times the length. If these two lengths are equal, then of course, area will be equal to T times L, and this is equal to H by root 2 times L, and therefore, the shear stress will be equal to P divided by twice H by root 2 L. So, this is the direct shear force which is acting on this joint, but what will be the effect of eccentricity? We see that eccentricity will try to rotate this entire plate about some axis, and what is that axis? This axis is nothing but the center of gravity, that is the geometric center of this welding. That is, there are two wells, and we can define always one center here, which is the geometric center. How do we define this geometric center? It is again based on the throat area. What we do here, we depict the entire picture, entire welding in terms of the throat area. So, here the length is L, and this one we look at in this plane. This is throat area plane. Now, this is T, similarly this is T and this is L, etc. Then the geometric center will be equal to, definitely because of the symmetry, this will be the center, and this is the CG of this welding. Now, because of the displacement shift from this CG by some distance E eccentricity, say, there is a tendency that this will rotate. Then how do you calculate the shear stress, that is the secondary shear stress because of this rotations or torsion? Now, we again have to make some assumptions. Again, the assumption is that here when it rotates, we get the force for every area, there will be some force. So, let us say for a distance r from this CG, let us consider this small area dA. We assume that this force again is proportional to the distance from the CG to that area. Of course, this assumption is almost similar assumption as that of the pure torsion of a circular shaft. We make these assumptions that the shear stress is proportional to that is varies linearly from the distance from the radial distance, that is varies linearly with the radial distance, that is it increases gradually as you go from the center of the shaft towards the periphery. Similarly, similar assumptions is made here. We make the assumption here that this force is now proportional to, that is F, or let us say dF, that is the small force acting over the small area dA is proportional to the distance r. So, therefore, we can write down that is dF, the magnitude is proportional to, this is the proportionality constant, proportional to r. and the area of course cross section. In a sense we say that the stress is proportional to R, and the forces of course will be also depending on the area of cross section. So, this is the total force acting on this infinitesimal area dA. So, therefore, the net torque will be equal to T, which is equal to dt will be equal to R times dF. The direction is again important. Direction is such that it tries to rotate. So, therefore, this direction of this force is perpendicular. So, this line, the direction of this force dF is perpendicular to this line, this vector joining CG to that infinitesimal area. So, therefore, the total torque will be equal to R times dF. So, this is the torque over this infinitesimal area. Hence, the total torque will be equal to the integral of this, and that could be written as K R square times dA, and this is over the entire area. Now, this is again, if you calculate it, then this will be equal to your, this will be equal to the torque, external torque, this is Pe. From this we calculate K. Now, if you write down this in details, what you get is K will be equal to the torque Pe divided by integral R square dA, which is nothing but the J of the total throat area, and hence we can calculate the maximum shear force, that is the shear stress will be equal to the maximum shear stress tau max, which is equal to K times R max, K times R max. So, therefore, K is equal to Pe R max by J. Now, J, how to calculate J? J is very easy to calculate. You know the geometry, from the geometry of this, we know these two well milled. If you have T, then L, and this distance is the total height, this length is equal to say B. From this you can calculate J, and J is nothing but so J is R square dA, which is equal to x square plus y square dA, and this is nothing but Iyy plus Ixx, and Iyy and Ixx, the second moment of area of these rectangles are easily known. Remember, T is taken to be very, very small compared to the other dimensions. So, therefore, the higher order terms containing T are sometimes neglected, and in the book what you get, there are some tables which are available which contains the value of J for unit thickness, that is we consider the T to be unity, but of course, this unity is again very small thing. So, therefore, we neglect many other higher order terms, and what you get the value for unit T. Now, whatever, then if you have this relationship, what you have to do is just take this data and multiply by the throat length, which is equal to root 2 h by root 2. H is the leg of the or the height of the fillet weld. So, if you do that, then you get J, then tau max will be equal to Pe R max divided by J. What you have now is that you have tau max, the direction of the force you cannot add vectorially to stresses, but you can add vectorially to forces. So, what you can do over a small cross sectional area, you can calculate F, that is the force dF due to the load, the direct shear stress and the shear stress due to the torsions, and then again you add vectorially and find out the maximum shear stress, and using the maximum shear stress theory you can find out the different design parameters. So, this is roughly the way how to calculate the welded joints when there are eccentric loading. So, let us recapitulate what we have learned. We have learned how to calculate the design, how to calculate the strength of joints with eccentrically loading for riveted joints. Here mainly the shear stresses exist. In the bolted joints, there may be cases where the only the tensile force appears, or there may be cases where both shear force and tensile force appears, and in eccentrically loaded welded joints there is a case where the shear stress will appear. Sometimes we can have tensile force, but there we are not going to discuss them. So, this is all about the eccentrically loaded joints. Thank you very much.
Let us begin the lectures on machine design part 1. This is lecture number 26 and the topic is design of joints with variable loading. In the last few lectures we have learned how to design the joint for strength for various static loadings. Now, in the last class we have learned how to design the joint for eccentric loading, and in this class we are going to study for the variable loading. Now, variable loading is very important for any machine components. In structural joints, normally the loading is static, but in machine components there will be invariably some movable parts, and because of this movement there will be the forces which are normally fluctuating in nature. So, these are to be taken care of while designing it.